All right, cool. Let's do it. So today we're gonna sort of like, so last time was this ILC conversation, which is like how we like one way of dealing with, modeling error, sim to real gap, whatever the kids are calling it these days. Um, the one that gets me, man, is really world models. Like it's a dynamics model. Like what is, I don't know, it's hilarious. Anyway, end of my old man rant for the day. I'll try. It is. But why do we call it a world model now? Like it's literally next state prediction, right? Like what do you call that? I call that dynamics. That's what we've called it forever. Why is next state prediction all of a sudden a world model? I don't know.
It's easy to
Weird.
raise funding with VC.
Huh?
It's easier to raise funding with VC.
Oh yeah, for sure. I mean, you gotta dress it up, you gotta use the lingo. I get it, It's all right. Okay, so ILC, we just had a whole conversation about, things you could maybe do with that. There's lots of fun things you can do with this. And yeah, frankly, like I'd be super into if anyone is thinking along these lines, like I would love to see doing this with like small MLPs, like neural network, but it's super fun. I think you could totally do some cool things with that. Anyway, okay, so that's cool. That's sort of still, I would say, very much in like deterministic land. It's coming from a deterministic viewpoint where, the world is deterministic. I have a model. It's just wrong. And somewhere out there, there exists a perfect model. Like in theory, a perfect model that can predict this does exist. I just don't know it. And I'm going to maybe collect some data and try to figure this out, right? So I think that's kind of that viewpoint. And today we're going to kind of veer off from deterministic land for kind of the first time in the course, actually. Like pretty much everything we've done so far has been from this very deterministic viewpoint of like, the world is not really random. Like you can model the world and like a model does exist. It might be hard to write it down or whatever, but it basically comes down to like the fact that I can predict what's going to happen, right? And today is the first time we're kind of taking a tiny step outside of that comfort zone and getting into stochastic land. So we're going to talk about today stochastic optimal control from a pretty high level perspective at first, and then kind of as we've done so much in the class, special case this to like the linear dynamics, Gaussian noise kind of setup, which is classically known as the LQG problem, linear quadratic Gaussian. It's the stochastic version of the LQR problem that we've studied so much and kind of look at how things change in the stochastic setting. We're going to do LQG only because it's tractable analytically and nice. And there's some classic results in there that you guys should know about. But in general, this is a super big area. And like this, particularly this stochastic setting is the basis for pretty much all of modern RL. So I want to teach you the basics and sort of like get you familiar with some of the key ideas. In particular, stochastic dynamic programming is like what we're going to talk about. It so happens that in the linear quadratic Gaussian case, you can actually derive closed form results from all that stochastic dynamic programming stuff. But in general, it's cursed and terrible and like just throw neural networks at it, I think is kind of the modern thinking. So I want to show you kind of the basics and then, you can run wild with it from there. Okay, so that's what we're doing today. Any thoughts or questions about that before we get into it? Okay, here we go. So stochastic control. And yeah, I just said this out loud, so I guess I have to write it now. So far, we have assumed we know the system's state. Perfectly. And sort of modulo modeling errors that we could predict it in principle perfectly, right? So now we're going to ask the question, what kind of at the root of all of this is what happens when all we have are noisy measurements of quantities related to the state, not even the full state, right? Which in practice, this is always the case. Like we never have direct measurements of a state. We always have measurements of random chunks of the state, and they're always noisy, and there's always issues with your sensors and blah, blah, blah. And then like, what do you do with that, right? So this is very practical also. Of quantities to the state. And sort of the prototypical scenario here is we have measurements y that are some function, in general, a nonlinear function of the state x, right? And this function is called a measurement model. So these y's here are measurements. And this g of y, or g of x function, sorry, is the measurement model. So this is kind of like, for instance, simple example would be like, let's say I have, I don't know, something driving around that's got a position and a velocity, and like I only have a GPS receiver that gives me the instantaneous position, right? So in that case, like g of x is like, basically an identity block on the position coordinates and then zeros everywhere else. So it's just picking off parts of the state. That's pretty common. There's other weirder ones, right? Like, I don't know, for instance, you have ranging measurements between multi-agent robots, and then you only have access to the range, which is some nonlinear function like a norm, right, of your position difference or something like that. So there's weirder examples. Could be anything in general. Yeah.
Does that include your like noise?
Not yet. We're getting to that right now. So there's different ways of accounting for noise. In general, the most general version of this would be like g of x, and I have to now go look at what letters I used for this so I'm consistent. But okay, yeah, so g of x comma v, where like v is a noise. And in general, this noise can enter in kind of arbitrary nonlinear ways. But we'll often assume that it's additive noise, that it's additive sort of Gaussian noise. So this kind of thing. And yeah, we'll get into more on that in a minute. So yeah, there is noise, and you don't get actual state measurements, right? Okay, and so everything we've done so far, we've assumed we have an x, and we can just do control on top of x. Now we only have y's. And so kind of what ends up happening here is before we were just like living with this nice x vector and we could do whatever we want. And now in this stochastic setting, we basically have to make do with a probability density function. So it's basically what we're going to end up working with is the probability of x conditioned on y. So I only have access to the y's. I want to know the x, and I want to do control based on the x. But this is all I've got, right? I'm going to collect a whole bunch of measurements y. I'm going to do whatever kind of filtering stuff I can do to get an estimate of x, but ultimately that's a probabilistic estimate of x. And it ultimately is there's some distribution over x. And that's really what we're stuck reasoning over, right? So this is like the key transition. We're going from having this thing to like where we just have a vector x to now this like probability density function of the state conditioned on the measurements. And so for those in the know who know the lingo, this is a POM DP, a partially observed, i.e. y equals g of x, right? So we have partial measurements of the state y, partially observed Markov decision process. The Markov thing is there's a state and you have a state transition, aka dynamics. And yeah, decision process means it has inputs, use, control. So that's the lingo, if you've heard that lingo before. Okay, cool. So now we're going to say, so this is kind of the setting. And now we're going to say, like, the problem we're going to end up solving now is a stochastic optimal control problem. And at a high level, basically all this stuff is about is we go in and write down, like, say before we had something that looked cartoony, like, this kind of thing. So we have our cost function, it's a function of states and controls, and maybe we have dynamics, whatever. But you have something like this. Basically, you take everything and you just wrap it all in expectations. So now instead of minimizing the cost, we're minimizing the expected cost, right? Expectation over this cost function. So it ends up just kind of, in general, just goes throw expectations on everything. And that's kind of the only real difference. And in principle, we can solve this kind of stuff with dynamic programming. So, and it doesn't actually change very much from what we've already seen of dynamic programming. It basically wrap it all on expectations and proceed as before. But there's a lot of gotchas. In general, this is super, super hard. The real issue comes from writing down that PDF and similarly writing down a value. We already talked about value functions and how they're high dimensional functions and in general super hard to write down for nonlinear things. And here, not only do you have the value function, which is like some function over the full state, you also have this probability density function. So even just writing down a probability distribution in high dimensional spaces and kind of dealing with them is super, super nasty and hard. The only really tractable case is Gaussians, where we can parameterize the whole thing by a vector for the mean and a matrix for the covariance. And that's sort of tractable, and we can do that. As soon as it gets nastier than that, like it becomes super, super hard to approximate and write it down. And therefore, neural networks or sums of Gaussians, which are now called splats, which are fun. That idea has been around a long time too. So there's all kinds of things you can do, right? But it ends up being like a really hard game of figuring out how to represent these high dimensional functions. And so that's kind of the problem. So it's basically back to the same story of cursive dimensionality, right? Like representing complicated functions in high dimensional spaces becomes super, super hard. Like the naive thing would be to grid the space and write down the value in all the grid cells, but gridding it blows up exponentially in the sort of dimension, right? So that's bad. Okay, so that's sort of sad story. Yeah.
How do you set the constraints for that problem? Because that also feels.
Yeah, so you can do it. So in particular, inequality constraints, you can write down in expectation kind of the very same way. That's called a chance constraint, if you've heard of that. Literally what it ends up being, so originally we had a function like c of x greater than equal to 0. You write down probability of c of x being less than equal to 0 has to be less than some epsilon. So you write down like the probability of violating the constraint has to be less than some epsilon. That's the gist. Those are called chance constraints. They're just probabilistic versions of constraints, right? So for inequalities, it's well defined and you can just do that. For equality constraints, it's sort of sketchy and there isn't really a great way to do it. Okay. Okay, onward. So what we're going to talk about, I'm going to spend a little bit of time on now, is the famous LQG problem. It's a special case that mercifully we can actually solve in closed form, very much like LQR that we saw before, but it has some new twists and turns that are fun and you should know about. Okay, and sort of as you might expect, L is for linear. Linear dynamics, that's the same as LQR. The Q is for quadratic costs, which is the same as before. And then the G is the new piece. This is for Gaussian noise. And so that sort of, as we were just saying, when noises are Gaussian, they have a nice compact representation that scales nicely with dimensions. So we can actually write down Gaussians in high dimensions and it's fine. So it's just a covariance matrix, right? Okay, so far so good. So here we go. So the dynamics then, they're very much like before, but they have noise on them now. They're stochastic dynamics. So we're going to have xk plus 1. And we're going to also, another fun thing about this is all of these things get really weird and mathematically complicated to do in continuous time. But thankfully, in discrete time, it's all nice and easy. So we're going to do everything in discrete time for all of this stuff. There's also the practical setting that's useful in real life anyway, so I don't feel bad about that. But it turns out defining noise processes in continuous time is super weird and crazy. So we're not going to try. Xk plus Bu. So this is what we had before, plus we're going to add a noise term. So we're going to call this one WK. This is called process noise. So it's saying our dynamics really is stochastic. I can't exactly predict the future given the current state. There's noise on it. You'll see slight variations on this. Sometimes you'll see a matrix in front of the W where it's like entering the dynamics in some specific way. I don't think that's a super big deal because you can always bake that into the covariance of the distribution kind of anyway. So there's technical reasons why you might want to do that, but I don't think it's a big deal. So this is called process noise. That's noise in the dynamics and the physics, right? And to be clear, some physics processes are really stochastic, right? Like Brownian motion kind of stuff, or maybe wind gusts where it's kind of random and unpredictable. So there are legit stochastic settings. Like, yeah, flying a drone around in gusts or something. Cool. That's kind of random. Legit. But many of the systems we encounter in robotics, they're really not stochastic. And what you end up doing in practice is saying, I'm going to use some crappy approximate model. I'm going to just say everything that isn't really modeled. I'm going to kind of try to absorb into the noise term and account for it that way. That's not quite legit, but it's done a lot in practice. And I want to kind of make a distinction between deterministic but poorly modeled, i.e., in theory, some model does exist that predicts the behavior, and actually stochastic, right? And these are blurred in practice because people very often use noise to kind of, in a very hacky way, account for modeling error. But there's a really rigorous distinction between deterministic but bad model, which is what we handled last time, right, in ILC land, and that was all deterministic, and actually stochastic, right? To be clear, right, if you have a real stochastic system, ILC won't work because it depends on reproducibility of the experiments to improve, right? So it's very important, I think, just to harp on that a little bit. Okay, and then we have also our measurement model, and that looks like we just had the general case y equals g of x. Here we're going to assume it's linear, so it's y is going to be some matrix C times x, and we're going to have Gaussian noise added on, and this we're going to call V, and this is called measurement noise. And really simple. So this is all in discrete time. So at every time step, I propagate the dynamics and I add on noise drawn from a Gaussian. And then if I take a measurement, I run my state through that linear function and I sample noise, a noise sample from a Gaussian. And we're going to assume both W and V at every time step are drawn from a Gaussian. So we write that like this. So process noise comes from a normal distribution with zero mean and covariance big W. And then similarly, measurement noise comes from a Gaussian, zero mean, big V. These are kind of classic assumptions. The reason we assume zero mean is the mean you can always kind of subtract off and it doesn't like change. This is sort of, without loss of generality, we can assume zero mean. Yeah. That's right. Yeah. Yeah. So in general, like it's not zero mean, but you can always estimate the mean and subtract it off in ways that are kind of trivial. So we won't bother with it here. And it's
noise is independent of the state.
exactly. Yeah. So that's another key thing that will come up later that I didn't kind of harp on yet. But yes, these are all assumed to be completely independent, like IID, blah, blah, blah. The samples are not core. The noise you're drawing is completely independent at every time step. It's just coming from a Gaussian. It doesn't depend on the state. It doesn't depend on the controls, et cetera, et cetera. Another way of saying that is if it is correlated with the state of the controls, that means you should model it and it should go in the model, right? Okay. Let's see. Okay. So, and then for those who haven't seen this, has anyone seen this notation before for distributions? Okay. If you haven't, so like what this means is this little squiggly thing in words is drawn from. So it's saying omega k is drawn from. So it's a sample drawn from the n is normal distribution, aka Gaussian. And then the first entry here is the mean. So we're saying zero mean. And the second entry is the covariance matrix. So that's the setup. Cool. Okay. Who in here has not seen a multivariate Gaussian before? Has everyone seen a multivariate Gaussian? You haven't? Okay. So I was planning on doing this now. I just want to get calibrated. That's cool. Yeah. Don't be embarrassed. It's fine. I'm not judging. Okay. So just for fun, for those who haven't seen it, and just as a quick recap, because this will come up a bunch. And these are also things you'll probably encounter in your life. So it's good to see it again. So this is a multivariate Gaussian. This is a normal distribution in more than one dimension. So the probability density function, this P of X thing, it's got a normalization constant out front that looks a little gnarly, but this is literally just normalizing the distribution to 1. So it integrates to 1. And it just looks like this. We're not going to derive this, or you don't have to care too much. So the n there is the dimension of the space, and then S here is the covariance matrix. So that's the normalization constant. It's not that hard to derive. And then this is what the actual function looks like. So I'm writing it like this. It's e to the stuff. So it's exp. Inside here, it's actually a quadratic. It looks like this, -1/2. It's x minus the mean. And then this is the covariance, the inverse of the covariance. And x minus mean. Cool. So that's what that looks like. And then we have a mean, which is we're going to, in this example is mu. We'll also frequently write that as x hat. We'll use a hat over a variable to indicate the mean. And we're also going to write it as the expectation of x. Cool. So that's what expectation means. We'll tell you a little bit more about what an expectation is in a sec. And this is a vector in Rn, just to be clear. And then the covariance. Above, we wrote this as S. It's a symmetric positive definite matrix in general. And this thing is equal to the expectation of x minus mu times x minus mu transpose. And this is a symmetric positive definite matrix. That's one way of writing that. So it's S for symmetric, N for n dimensions, and then the plus plus means strictly positive definite. 1 plus means positive semi-definite. Plus plus means strictly positive definite. So that's what we want for covariance matrices. And then just to make it super explicit, what we mean by this expectation-y thing. So this thing, so the expectation of a function of x is equal to the integral over all space. So like minus infinity to infinity in every direction of f of x times p of x, the probability density function, px. So basically to compute an expectation of some function, you take the function, multiply it by the probability distribution, and integrate over everything, right? So if you do that for just x, that's the mean. If you do that for like x minus mean squared, that's the covariance. And there's lots of this. You can take expectations of anything in general, but those show up a ton, right? And for a Gaussian, it's uniquely determined by the mean and covariance, aka the first two moments, or expectation of x and x squared, that kind of thing. Okay, most of you hopefully seen this before. Quick review. Any questions about this?
Dimension of the state as a Gaussian.
So you can get there. It's a little, so if the covariance matrix is diagonal, then it does decompose into a bunch of one-dimensional Gaussians for each element of the state. In general, though, if the covariance is a sort of full matrix, not diagonal, then what that's really telling you is there's like kind of correlation or mixing across the states. But there is some basis in which you can diagonalize it, in which case it is decoupled, right? But that might not be your initial state vector or whatever, if that makes sense. So another way of saying this is every symmetric matrix is a diagonal matrix that you're looking at crooked. So every symmetric matrix is a diagonal matrix in some rotated coordinate frame. So there's some state, you could do a change of variables into some different state vector where it would decouple into a diagonal covariance, but that doesn't necessarily hold up because the dynamics can cause mixing, right? If I have an A matrix the A matrix can mix my states around, right? And then that can sort of, now you're not diagonal anymore, right? So you could diagonalize it at one instant in time. And if the dynamics were decoupled, you could decouple it, blah, 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 lots to say about this. But in general, it's not the case, right? Okay, any other questions? Okay, excellent. So we've got dynamics, we've got Gaussians. Those are the key ingredients. So now we'll talk about the cost function. So it's a quadratic cost, like we're used to. And like we said before, we're literally just going to slap expectations on everything. So we're going to have our standard kind of LQR cost situation. So I'm going to just write it as like we've got our terminal cost term. And then we've got our sum over time. So k equals 1 to n minus 1. And we're going to try to keep things as simple as possible here. So xk transpose qxk, uk transpose r uk, move the 1/2 out. Cool. So that's the normal LQR cost. We've just wrapped it in an expectation now, right? Okay. So now it's time to get down to business. We're going to start we're going to basically go through the dynamic programming recursion that we did for LQR, but now there's going to be basically expectations on everything and noise terms to worry about. Okay, and we're just going to turn the crank on dynamic programming. Shouldn't be any surprises. It's literally the same recipe as before. There's just some extra terms now because of the noise, and it's all inside an expectation. So we're going to have to think a little bit about basically what this comes down to is the same derivation as before, but you have to start thinking about everything as a Gaussian inside an expectation and like some little tricks for dealing with Gaussians. that I'll kind of like try to tell you about as we go. So here we go. DP recursion. So we're going to start at the end. So we have Vn of x. So this is the value function or cost to go function at time n at the end of the trajectory. And this looks like, ooh, that was weird. So again, same as usual, but wrapped in an expectation. So it looks like xn transpose qn xn, right? It's just the last terminal cost because there's no control move. So that's it. And as before, we're going to sort of call that that Hessian Pn. So we're going to write this as xn transpose Pn xn. And now we're going to do our Bellman backup thing, go back a time step, write this all out. And at the end of the day, what we're trying to do is come up with a recursion for P, right? Okay, so let's do that. So now we're going to go back one time step, write Vn minus 1 of x. And this is min over u of the expected one-step cost plus sort of cost to go term, right? So let's write one-step cost in there is xn minus 1 qxn minus 1 plus un minus 1. I guess this is, to be super pedantic about it, I'll leave the u with no subscript. I'm doing un minus 1 is the actual u, which would be the argument of this thing over u. None of this is important. This is just me being slightly careful. I'm usually pretty fast and loose, but try sometimes. Okay, so there's that. And then we have our dynamics to propagate to the next time step, and then the Pn, right? So before this would have just been AX plus BU. But now we've got the noise in there as well. So this is WN minus 1. So this all gets mapped, this is just mapping us to time step N. And then we've got the cost to go kind of set up from that time step. Okay, so that's the whole thing. So this looks exactly the same as before with two modifications. Modification number 1 is the whole thing's wrapped in an expectation. Modification number 2 is now there's those W's in the dynamics. If you took those two things off, it's exactly the same as the LQR stuff from weeks ago, I guess now. Cool. So now we're going to try to, what I'm going to do next is basically like group these terms in a suggestive way. So what I'm going to do is I'm going to group all the stuff that's vanilla LQR. I'm going to pull that all out and group that together. And that part's the same as LQR. Then I'm going to group all the noise terms together into another group. And that's the new stuff. That's the stochastic stuff, right? So we're going to do that next, because that's going to sort of hopefully be somewhat illuminating. Okay, so and the other thing to mention here is that expectation is a linear operator. That means that I can kind of pull things out and in and out of the expectation. It's linear, right?
Does the fact that the noise term is like squared because
Yeah.
it doesn't just come out to 0?
Yes,
Okay.
that's a very good observation. Yeah, so if it were just by itself, it's 0 mean. So the mean, so expectation of W is 0, right? But expectation of W squared is not 0. That's like covariance E stuff, right? So very good catch. That's 100% coming up. Okay, so yeah. So this is actually a very subtle and important point. This shows up in least squares all the time. So if you do linear least squares and you have noisy stuff, because you square the noise actually biases your estimates. This is like a totally, so this is a weird kind of thing that shows up in very, very benign applications that like you kind of have to be really careful of actually. It turns out if you're doing any kind of nonlinear estimation stuff, you're going to get biased estimates because the noise gets sort of squared and things like that. And then it doesn't average out to 0, right? Fun fact, I don't know. Okay, here we go. So yeah, good call. Here we go. Thank you. Okay, so let's keep trucking. Okay, so this is sort of we'll call, quote, the standard LQR stuff. And this we know what to do with. And then we're going to end up with another term here. And right, because expectations linear operator, I can pull stuff out and I can separate this thing into two chunks. Okay, so here's the noisy stuff. So we're going to get following stuff. I'm just like foiling that thing, right? This would just be U. Transpose Pn Wn minus 1. And then I'm going to get it the other way. And then I get a term like this. Okay, so as was already very correctly pointed out to us, that last term is not 0 because it's kind of squaring the W. So there's some covariancy stuff that's going to pop up. How about the first two terms? What's going to happen with those? So I'll label this one. So this is, we'll call this sort of noise terms. What's going to happen with the first two? Yeah, why? Yes, yeah. And because basically, okay, here's how to think about this. The expectation's over W, right? It's over the noise. As far as the noise is concerned, everything in front of the W in that is a constant, and I can pull it out of the expectation. So it's basically a bunch of stuff times expectation of W, because expectation is linear, and those are not getting integrated over in the expectation. So that looks like stuff times expectation of W is 0. Another way of saying that, which you were very correct about, is that the state at time k is uncorrelated with the noise at time k, right? At every time k, I have a state, I'm already in that state, and I'm going to sample a random noise vector W from a Gaussian. That has nothing to do with X, right? At the next time step, xk plus 1 does depend on Wk from the last time step, right? So future states are correlated with past noise because they've gotten propagated through the dynamics, whatever, and they're kind of getting integrated up in like a random walk kind of way. But the current state is completely uncorrelated from the random draw at that current time step, right? They're totally unrelated things. So that's kind of, yeah, another way of saying this uncorrelated business. The easiest way to say it, though, is the expectation is taken over W. So all the other stuff there is constant with respect to that expectation and pulls out as just a matrix on the outside of the expectation. And then I've just got expectation of W's, which is totally 0. The only term that sticks around is that last one where I have an expectation over like a W squared, which is going to be non-zero and depend on the covariance, the big W. Does anyone know what it is? There's a trace trick thing in there that we'll do it later, so don't worry. Okay, so let's write that down. Basically, this stuff all ends up being 0. And then this term at the end ends up being a constant that is basically just P times big W at the end of the day. It's essentially Pn times the covariance matrix of W in some kind of way. Modulo, matrix stuff, but that's basically what it is. So, okay, so that's cool. That the math, the algebra of this, I think is hopefully clear. The implications of this, though, are kind of deep, and we're going to talk through them and be a little bit careful about them. So let me write some stuff down. So first thing to write down is what I said out loud, basically, the noise sample drawn at time k has nothing to do with the state. Or control, actually, right? Because if I have a feedback policy, it's, U equals k of x or something like that. That U depends on xk, which is already whatever it is. So the way to think about it is like in terms of like determinism here is I know the state right now. That's my state. I'm going to figure out what my control move should be based on that state. And then the noise is kind of getting added on in the transition to the next time, right? So I don't know what that is yet. And it has nothing to do, kind of causality wise, has nothing to do with the state of the control at this time. time k. So yeah, xk does depend on wk minus 1. It depends on past noise and all previous noise, right? And all previous w's. But not on future w's, which is kind of obvious if you... Okay, so that's kind of the story there, and that's why those terms are 0. And to be a little bit more, rigorous about this, what does uncorrelated mean? It means that the cross correlation between those vectors is 0. So like if I were to make a big joint Gaussian over like xk and wk, if I stacked xk and wk into one vector, and then I wrote down that expectation of both of them, right? The cross correlation thing, the outer product thing, the covariance matrix of that joint Gaussian, there would be no cross terms. The Gaussian would decouple into two separate blocks. The covariance of that would have two blocks with no cross terms between them. That's what uncorrelated means. It means the cross correlation, the off diagonal terms in the covariance matrix are 0. That makes sense to everybody? So basically what that means is the Gaussians factor apart into two separate Gaussians, and there's no crossover between those variables. Another way of saying that is knowing one doesn't tell you about anything about the other. Because they're sort of all saying the same thing. Okay, any questions about that? So far, so good. All right, cool. So let's see. Yeah.
Mentioned measurement noise before.
Yes.
Are we assuming measurement noise is also independent of the process noise?
Yes. Yeah. Everything's like IID drawn from a Gaussian at every time step. Has nothing to do with the past or future kind of stuff. And it's just the noise is whatever it is. It's completely a random draw at every time. And it's totally independent. Yeah. No, that's subtle. So the state covariance can be whatever. It's like fully dense matrix. The noise covariance can be a fully dense matrix. What we're saying is the cross covariance between the two. So in this case, x and w is 0. So what that is saying is if I were to stack x and w into one big vector, call it z, and then I wrote down the covariance matrix for z, that covariance matrix would have two diagonal blocks with nothing in the off diagonal between x and z. So it's saying that x and z have no cross coupling. Knowing one doesn't tell you anything about the other. Another way of saying is that the distributions, the Gaussians there are totally, can be factored apart and like have nothing to do with each other. Does that make sense? Cool. Anybody else? Okay. So if you've never done this kind of statistics stuff before, this is maybe a little bit out of your wheelhouse. So definitely speak up and ask. And like, it's not stuff we've done here quite yet either. So, okay. So now we're going to get into like interpreting this a little bit, and this goes deep and is really interesting. So what this is really telling me here is, okay, so I split these terms into noise terms and LQR terms. I have LQR at the top there. I know exactly what to do with that. The solution is the Riccati stuff, and I get a K matrix. The second term there is kind of all the stuff to do with the LQG, the noise part. And what it's telling me is those first two terms drop out and are 0, and the last term is just a constant. So what does this tell me about the control policy? It changed, nothing changed. So what this is telling me is basically, at least with additive Gaussian noise and linear everything, basically the move is to proceed as if it were not stochastic at all. The LQR controller is still optimal. All that happens is your cost gets worse, and there's nothing you can, what this is really telling you is that your cost is going to be higher and there's nothing you can do about it. You just have to eat it, and life is hard. That's basically what's going on here. And that's kind of a deep result. Yeah.
That cost like you're uncertain, which means your cost might be worse and you can't do anything about it.
You can't do anything about it. Like there's a certain amount of randomness here that you can't do anything about, and it's going to jostle you around, and you're going to get knocked around, and that therefore is going to make your cost higher. But you can't do any better. This is saying this is the best you can do. The best you can do is, and literally what it comes out to, and we'll do the rest here, but this is literally saying the best you can do is do LQR on the expectation on your expected state. So you run a state estimator, you get an X hat, which is your expected X, and you do LQR on that. And that's the best you can do, and your cost will be worse, but you can't do anything about it. So let's write some of this down. So that's a deep result, actually, that, okay, so let's say noise term has no impact on the controller, or no impact on the control design, let's say. And basically, you just get a higher cost. Okay, so this idea where so there's two things we're going to now define that are kind of big high-level control theory ideas. The first is called the certainty equivalence principle. Has anyone heard of this before? Nobody? Okay, cool. It's basically what I just said. So this is the fancy word for it. Okay, so what this says is, and this is specifically for the LQG problem, it says that the optimal LQG controller is just LQR, where we replace X with expectation of X. So we just do Riccati, we get our LQR stuff. And then online, we just plug in our best estimate of X instead of the actual X. So we plug in the expectation of X. That's why we call it certainty equivalence. Basically, the controller is just whatever it was as if it were deterministic. We just throw in, our best estimate of the actual state online, and that's it. So that's certainty equivalence. Cool. We'll have more commentary on this in a minute. And then the other kind of like big sort of control theory thing here is the separation principle. Has anyone heard of this? Okay, cool. Separation principle. These are related ideas. So the separation principle says that for LQG, we can design an optimal feedback controller, aka LQR, and we can design an optimal state estimator, aka Kalman filter, separately without thinking, one doesn't have to think about the other, and then we can hook them together at the end and we'll get the optimal answer. So it's saying you can basically separate the problem of optimal control and optimal state estimation, and that they can be completely decoupled and reasoned about separately. And there's separate classes on these things, right? And we generally think about them as separate things and then hook them together. In general, that's not true, actually, right? So let's write that down. So for LQG, we can design an optimal feedback controller. And an optimal state estimator. Separately. And then just hook them together. And the resulting of that, the resulting closed loop feedback policy is optimal. So that's like kind of nice and a little bit surprising. And then the punchline to this is that neither one of these results holds in general. And let's talk a little bit about that. So neither holds in general, but we still often do these things in practice. I would say like almost every single robotic system, I mean, you've never heard of these two things, but how often have you written a Kalman filter, an EKF, and used it on a robot with some other weird controller on a nonlinear system, right? We do it all the time in practice. So like, it's in general suboptimal, but this is, what we do still. And it's easy to come up with scenarios where this breaks. So let's talk about that. So examples, okay, so kind of what this is getting at the heart of this, when this breaks down, what you end up with is, who's heard of like the exploration versus exploitation trade-off? Like a lot of you probably heard of this. So anyone want to like tell me what that's about?
There's like a balance that you need to strike between taking paths that you know are good versus looking at other paths you don't know much about to see if they're better.
Yeah, so there's another kind of way of getting at that, which that's right. There's a subtle, okay, so here's a slightly different take on that, which is that often you actually have to take control moves to push the system into states where things are more observable. So there's like, you can easily cook up scenarios. Like a classic, really trivial one is, let's say I have like a 1D sliding brick and the goal is to drive it to the origin. But let's say all I let you measure is the absolute value of the position. So you don't know if it's on the left or the right. What do you do? So the only way to tease that out is you have to push on it with maybe a random action. So let's say you don't know if it's left or right. You make a hypothesis, push to the right. If the measurement goes up, you know you were on the right. If the measurement goes down, you know you were on the left. And then you can act accordingly. But if you add noise on top of that now, and the measurements are noisy, now it gets really hard. So you have to like sort of try to estimate if you're on the left or the right. And you have to do like hypothesis testing. And so basically what ends up happening here is there's a coupling between your control action and what you can measure. So your ability to figure out where you are is actually dependent on your controls. So you can't decouple your state estimation from your controller anymore. Your controller needs to reason about, said another way, the controller can't just reason about X anymore and have this decoupling where you just throw an expectation of X. Your controller actually has to reason about the full probability distribution over X now and make hypotheses about, like in that case, right, whether you have the absolute value measurement. Now, if I just give you a single measurement, you have equal probability of being on either side. So the PDF now is like bimodal, right? And so what's expectation of X is right in the middle. That tells you nothing, right? So like you have to now reason about the distribution in a deeper way, and you have to act in a way that depends on your uncertainty, right? And try to tease out where you are now. So that's the exploration part. Like you actually have to have control moves that are informed by your uncertainty and your probability distribution, rather than just mean of X. Does that make sense? Okay, and that's hard. And that basically means you have to now do like the dynamic programming thing or something that's actually reasoning over a probability distribution somehow, which is now a way higher dimensional thing to worry about. Okay, thoughts, questions, comments?
Just like from where we got that the cost, like the V of Vn minus 1 looks like standard LQR plus noise terms.
Yeah.
Does the separation principle like fall out of this point that this is
Yeah, basically it's saying like this noise term doesn't do anything to the controller design, right? It's saying like literally it's just standard LQR plus a constant offset on the cost.
if it were doing so, then like what would you do with it? Like in the
Yeah, so it's if you tweak this setup even very slightly, you'll end up with basically W's coupled to X's and U's in such a way that like the answer, like basically imagine I had in here something where I had like if I had some quadratic thing in here anywhere where like I ended up with W times U, now like if I do the min over U in this, the answer I get, like the particular control I get will depend on W. And that's a scenario where now you actually have to, the controller depends on the distribution over W, right? So it's very trivial to cook up examples where that happens. Like this is a special case. Like this is the exception to the rule. Like almost anything you put in here, like slightly more complicated distribution, slightly more complicated dynamics, you're going to end up with cross coupling between the noise term and the control term and whatever. And now this breaks and you no longer have the nice clean separation. Yeah. This is going to, yeah, sorry. Ignore that. So literally that ILQG thing that came from like Emo Todorov and like the ILQR papers, it makes zero sense. And it like, there's no G in any of that work. Like there's no noise, there's no anything Gaussian, whatever. It's a misnomer. It's ILQR. I have no idea. This is a 20-year-old random quirk of paper title that has somehow like continued in weird ways. Like it's, I would go so far as to say it's like confusing and ill-informed, and it has nothing to do with this. It's just ILQR in those papers. Okay, yeah.
So speaking of papers, how does guaranteed margins for LQG regulators fit into this whole picture?
Yeah. So what that's saying is that if there's uncertainty in A and B, so this is now a robust control setting. So that's saying I don't really know the dynamics or the measurements. So in particular, I have these A, B, C. Oh yeah, wrong thing for scrolling purposes. So up here where I have the A, B, and C, what that paper showed is that for arbitrarily small, for certain systems, where I can set up a scenario where I have arbitrarily small perturbations to A, B, and C, aka small errors in my dynamics model, or small sim to real gap, arbitrarily small, that can drive the closed loop system unstable. So the whole field of robust control was kind of founded on that idea that like, it turns out LQG, aka Kalman filter hooked up to LQR, it looks beautiful, it's really clean and nice, but there are certain like, I wouldn't even call them corner cases, because you can engineer systems like where this property kind of shows up, where you can basically be arbitrarily close to unstable. And so for very small errors in the model, the system will blow up on you. And so robust control was basically trying to figure out how to like sort of tweak this kind of LQG stuff in such a way that you could guarantee safety margins, basically guarantee that the thing would still be stable under like sort of bounded perturbations on A, B, and C. Does that make sense? Cool. And the modern RL version of that is domain randomization. It's like you train the policy with lots of random perturbations in the dynamics and stuff, such that the policy isn't sort of super sensitive to the model uncertainty. Cool. Okay, yeah, that's a bunch of good stuff. Okay, so these things are kind of deep. We always do this anyway, even though it doesn't hold. It's suboptimal, whatever. And I think one sort of like engineer thing to say about this is that when you sort of do this, what it really comes down to in terms of just working, forget like optimality, for this to work out, you're basically saying that I have a state estimator that's essentially passing expectation of X, just a single state vector over to the controller. For that to hold up and work, going back to also this absolute value example, it basically means your state estimate, your state distribution needs to be unimodal. If it's unimodal, you're kind of okay. And like things will kind of work out. If it's bimodal, you're kind of screwed and this will not work. That's kind of, I think, the practical engineer version of that. And then the also practical engineer corollary to that statement is if you're in a scenario where your sort of state estimate is not unimodal, probably you should just add more sensors until it is, and like not really try bothering with really fancy, crazy like particle filter stuff or whatever to sort of deal with that. That's a kind of a bad situation. Like if you don't know where you are, you're in trouble, I would say, in a practical engineering situation. So practically speaking, you want to be unimodal. And if you are unimodal, you can get away with this separation trick. Means one bump. Your probability distribution has one bump and you're at the peak, you hope you're at the peak of it, but you're not you're not maybe like the absolute value setting, right? Where I give you one scalar measurement, you have equal probability of being on the left side or the right side. You have no idea. That's a bimodal distribution. That's two bumps and you have no clue, right? So in that case, okay. So we have some time. So maybe I'll start like easing into what we're going to do next. Next, we're going to talk about state estimation. We're going to do a tiny bit of state estimation just to finish the story. Yeah.
Like systems integration
Yeah.
standpoint, like you could always just tack on more and more and more sensors to get this distribution down. So like
Yeah.
from practicality standpoint, isn't it always you can stack on as many sensors as you need?
Not always. I mean, there's scenarios where it's hard. Like a really good one that I've seen like really good work in the state estimation world where it is truly multimodal and gross is underwater navigation for underwater vehicles, autonomous underwater vehicles. So you can't get GPS signals or anything through the water. And what they do is they have maps of the seafloor. They have like topographic maps, so they know the topography of the seafloor, and they have sonar. So what they do is take sonar readings off the bottom and look at the seafloor, and then they try to map, do map registration and match that up to a map. And if you just have like a pretty local view of the seafloor and you get some terrain thing, like if you don't have a big field of view, that can match to multiple places on the map. So you actually end up with like a very multimodal distribution over where you are. And you can't do anything about it, right? You're just inherently limited. So what they do in practice is they have an IMU on board, so they can measure, how far they're moving from time step to time step. So they basically like drive around collecting information, and they use particle filters. So they keep track of a multimodal distribution, and as they drive around, they converge to some unimodal thing. But until they get enough data, by driving around a lot, they don't know. And it is truly multimodal, and you have to keep track of multiple modes in order to like converge, right? So that's an example. So there are hard scenarios where it's just hard and you have to live with it. But yeah, I don't know. If you can avoid it, you should avoid it. Okay, cool. So let's talk a bit about then like, so what we're going to get into next is this idea of optimal state estimation, just to kind of finish off the story. And we're going to do this next time, I guess, because of where we're at. Also, by the way, I very much enjoy the dialogue. So definitely like show up and like speak up. It's more fun this way. I like, this is good. I'm happy to go off the rails and, whatever. And it's much better. It's much more fun. I don't want to just like talk at you all. Otherwise, you could just watch the YouTube videos. Like, why show up? So, Okay. So anyway, okay. Optimal state estimation. The question here is like, what is optimal? What should I try to optimize? And this is related to our conversation about multimodal stuff. So let's draw like a very generic looking probability distribution, which is why we're talking about it now, because I feel like it fits the flow of the story. Okay, so we have like some random thing. I've got X, look, this is 1D. I'm going to cartoon a probability distribution, right? So let's say it looks something like this. Very generic, whatever. Okay, so if I have something like this, what is, like, this is the PDF. Like if I'm talking about optimal state estimation, I have to give you a state vector. What should I be going for here? Like what's optimal? Peak of the distribution? Very reasonable. Okay, so that's one option. Let's draw that. So that would put me here. Does anyone know what that's called? That's called a map or maximum a posteriori estimate. So let's write that down. That's completely reasonable and like a good choice, right? Does anyone have another idea? Yeah, so when you say center, do you have a tight definition of that? Yeah, that's totally right. So what's that called in probability speak? The mean. Yeah, it's the mean or expectation of X or whatever, right? Yeah, so that's what it is, to be clear, right? You're right. It's just, there's a word for it. So this map thing, this is the peak of the distribution. It's also, you would call it argmax of P of X, right? Just find me the max of that P function. Okay, so the other option is what you just said. I mean, you could make up other things, but these are kind of the two sane options that I would say are common in what everybody does. And that one is the like lingo for that. And if we were to do that in this scenario, that'd probably come out somewhere around here. Just cartooning, right? Okay, so that's called the MMSE estimator, or minimum mean squared error. That's a big kind of mouthful. What that really says, that's least squares. That's what that means. So it turns out the like expectation or center of mass or whatever of this probability distribution, that turns out to be what least squares does, and it minimizes the squares of the error. That, if I were to write that down, that would be sort of, that estimate would be argmin of kind of the expected, it's X minus sort of, let's call it, I don't know, X tilde or X, I guess it's supposed to be X hat. Yeah, so it's, seems good. So this is like, if I minimize this thing over X hat, right? So the X hat that minimizes this thing where that's the expectation over X, to be clear, right? Is the one that this is least squares, right? Okay, cool. So these are kind of the two options that are common. And to be clear, right, if I have some weirdo distribution like this one, the MMSE estimator can actually be bad, right? Like if I have a multimodal thing, that can be in a very low probability in the middle kind of situation, like back to the absolute value example, terrible. And in something like that, a map estimate is probably better. Here's the question then. How about for a Gaussian? Oh, you had something.
Oh, I was gonna say, wouldn't the map estimator like potentially give you either one?
Yeah. And there's, I mean, life is hard. I don't
Yeah.
know. It's a bad situation. You don't want to be in that situation. That's why add more sensors. So, okay, what happens if it's a Gaussian? They're the same. So basically, this is in general a hard thing to think about. And like if you're doing some particle filtery thing or something more complicated, you do have to make a choice here. In the case of a Gaussian and the situation we're in and the Kalman filter, which we're about to get into next, they coincide. And so you can actually derive the Kalman filter either way. You can minimize either objective and you'll get the same answer because for a Gaussian, they're the same point. Let me write that down. Okay. And at that, we're like perfectly on time. Amazing. That's what happens when I show up on time. All right, guys. Yeah, I'm happy to hang out for a bit though. Thanks for coming out. Oh yeah, I did. Thank you. Okay, cool. See you next time.